All right, let's start out with a basic definition of acids and bases and a summary of pH. So first of all, we have three major definitions of acids and bases: Arrhenius, Brønsted-Lowry, and Lewis. An Arrhenius acid is one that increases the hydrogen ion or hydronium ion concentration. For example, HCl in this reaction, where we end up with a product that's increased the H3O plus concentration. Okay. An Arrhenius base is one that increases the hydroxide ion concentration. In this example, where NH3 is acting as a base, we end up with this increase in hydroxide as a product. The limitation of the Arrhenius acid-base definition is that the reactions are occurring in aqueous solutions only. So this has to take place in water. You see how we have water as a reactant. Okay. A Brønsted-Lowry acid is one in which a proton is donated, an H plus ion is donated. So for example, in HCl here, acting as an acid, it's giving up that proton to become just the chloride ion. If the acid is the donor, then the Brønsted-Lowry base is the proton acceptor or the hydrogen ion acceptor. So in the same reaction, now instead of the HCl, we have the NH3 acting as the base because it accepts that extra proton to become ammonium. The limitation here is that the H plus ion, the hydrogen ion or the proton, has to be transferred. Okay. Finally, the Lewis acid-base definition is one in which an electron pair is transferred. And so in an acid, the Lewis acid is the one in which the electron pair is accepted. So in this case, if we have BF3 plus F minus, BF3 acts as a proton acceptor to form BF4, electron acceptor. So here BF3 has only 3 bonds. Here BF4 has 4 bonds, which means additional electrons. So it's acting as an acid in that it's accepting a pair of electrons. The donor is the base, and in the same reaction that would be the fluoride ion, where it's donating electrons to that boron in the creation of that 4th bond. And there's no limitation here to the Lewis definition of acids and bases. All right, so when an acid and a base react, they always yield what are called conjugate bases and acids. So in general, if I had this acid plus a base, once the proton in this case is removed, I get the conjugate base plus the conjugate acid, where the proton has been accepted. So as an example, HNO2 is an acid. Here water is going to act as a base. Once we remove that proton, we form the conjugate base. So an acid forms a conjugate base, and the base here accepts that proton to form the conjugate acid. In summary, after the acid donates a proton, the result is called its conjugate base. After the base accepts a proton, the result is called its conjugate acid. pH is a measure of the hydrogen ion concentration, or H plus concentration, in a solution, where the concentration is measured in moles of hydrogen ion concentration per liter, or molarity. The pH scale ranges from 0 to 14. pH is defined as the negative, and we can see the equation here, negative base 10 log of the concentration of hydronium ion, or often simplified here to hydrogen ion. Okay. If the hydrogen ion concentration is as given, times 10 to the minus 1, times 10 to the minus 2, times 10 to the minus 10, here are the pHs, 1, 2, and 10. So hydrogen ion concentration and pH share an inverse relationship. That means the greater the hydrogen ion concentration, the lower the pH. Because of the base 10 logarithm, each 1-point value on the pH scale differs by a factor of 10. So a solution with a pH equal to 9 has a hydrogen ion concentration that is 10 times more than a pH 10 solution. A solution with a pH of 8 has a hydrogen ion concentration that is 10 to the second or 100 times more than a pH of 10 solution. A solution with a pH of 7 has a hydrogen ion concentration that is 10 to the third or 1,000 times more than a pH 10 solution. All right, let's talk about this special equilibrium constant for water, the ion product constant for water. So water, we could take two waters and it'll dissociate, and we can get the hydrogen ion or hydronium ion plus hydroxide. And at 25 degrees, so K water, we know, is the concentration of the products over the reactants, but we have pure liquid, so it'll just be the products. Hydronium ion concentration times hydroxide ion concentration. At 25 degrees Celsius for water, this value is 1 times 10 to the minus 14. This is a very small number. Because of that, we can conclude that pure water contains relatively very few ions. In pure water, the hydronium ion concentration and the hydroxide ion concentrations are equal, which means that they have to equal 1 times 10 to the minus 7 molar. All right, so how do we calculate that or translate that concentration into pH? So pure water has equal hydrogen and hydronium ion concentrations of 1 times 10 to the minus 7, which results in a pH value of 7. If you increase the hydrogen ion concentration, then the solution becomes more acidic. And if you increase the hydrogen ion concentration, we've already said that's an inverse relationship with pH, so the pH decreases. So if you have greater hydrogen and less hydroxide ion concentration, you have an acidic solution. There are excess hydrogen ions in the solution, and the pH will be less than 7. The opposite is true if you decrease the hydrogen ion concentration and increase the hydroxide ion concentration. You get an excess of hydroxide ions in solution, and we call the solution basic with a pH value greater than 7. Here are some pH values for several common substances. So very, very low on the pH scale, most acidic gastric acid, but it's similar to the citric juices, coffee, urine, and then distilled pure water would be right in the middle at a pH of 7. Some of the most basic of substances: bleach, soapy water, ammonia, milk of magnesia. So we use that basic substance to calm and acid, right? Baking soda or seawater is slightly more basic than pure water. How do we calculate pH? So for example, what is the pH of the solution with hydrogen ion concentration of 5.67 times 10 to the minus 8 molar? So here's our equation where pH equals minus log of the hydrogen ion concentration. First, we need to take the log of the concentration. When we do that, we get minus 7.246. Then apply the negative. So multiply this by a negative, change the negative to a positive, and we get a pH of 7.246. If you tried to take the log of negative 5.67 times 10 to the minus 8, in other words, apply this negative on the other side here, you would get an incorrect answer. So the order of operations is first to take the log and then to switch the sign. There are a couple of additional calculations we might have to do involving pH. First, if you're given the pH and asked to find the hydrogen or hydronium ion concentration in the solution, we have to do the inverse of the log. So here's how you do that. If the pH is equal to the minus log of the hydrogen ion concentration, then the hydrogen ion concentration is equal to 10 to the power of minus pH value. So what is the hydrogen ion concentration in moles per liter in a solution of milk of magnesia whose pH is 9.8? So the hydrogen ion concentration equals 10 to the minus pH value, or 10 to the power of minus 9.8, which is 1.58 times 10 to the minus 10 molar. There's another value called pOH that is closely related to the pH. The pOH tells us to take the negative base 10 log of the hydroxide ion concentration in the solution. pOH is equal to minus log of the hydroxide ion concentration. We know the relationship between the hydronium and hydroxide ion concentration through this K water, 1 times 10 to the minus 14. So that means that the minus log of the hydroxide ion concentration, or the pH, plus the minus log of the hydroxide ion concentration, which is pOH, is equal to the minus log of K water, which the minus log of this value is 14. We call that the pKw, or it's equal to 14. Here's a little flow chart to just help remind you what to do for these pH concentrations. So if you have the hydrogen ion concentration and you want to find the pH, it's the minus log of that concentration. The reverse would be 10 to the minus pH value. Same thing for pOH. If you know the hydroxide ion concentration, you take the minus log of it to find the pOH. Or if you know the pOH and you want to find the hydroxide ion concentration, it's 10 to the minus pOH. Now, the relationship between pH and pOH, the sum of those two must equal 14. And for the hydrogen and hydroxide ion concentrations, the product of those must equal K water, or 1 times 10 to the minus 14.